Hello, everyone. Welcome back. I hope you all had a good weekend. Um, a couple of things before we get started. Number one, the homework. You probably saw my announcement, and we're running a little bit behind with this binary tree stuff that we're doing. So what we're going to do is we're going to extend the homework number 5 to be due on this Sunday. I think we'll be finished with binary trees by then, and you will have homework number 6, which will be the next homework, which has got to do with binary trees. Um, any questions on that?
Is homework 6 the last homework, Professor?
We'll have to see.
Okay.
We'll have to see. We're not sure. Okay. Whoops. There's a hole in my shirt. Um, okay. Um, anything else? Any other questions? Okay. So let's get started here, and we're gonna try to get through some stuff with the binary trees today. Um I'm gonna go back to doing going back to share my screen with you, and then we will proceed from there. Okay, so we're gonna do this. Uh, let's get rid of this off the screen here. Uh, no need to have that here. And we'll come back to it. Yeah. All right. So we were in the main routine over. We were in our driver. We had created a main method that created people, and then created a binary search tree and inserted all the people in here. Now we want to see what our binary tree looks like. So we're gonna write a method to go through our method, our binary search tree, static void traverse. Uh, and where we're going to traverse is a binary search tree. Uh, search tree person, integer, comma, integer, and tree. Okay, the tree is called tree. Okay. What's the problem over here? It's key value. I see. It's not value key. Sorry. Uh, key value. Okay. And we're gonna the way we do that, we do a tree iterator. We wrote the iterator, and that is also takes an integer key value pair. Iterator is equal to tree dot iterator. Okay, we have an iterator. Okay. And we have to cast this into, because it returns an iterator, tree iterator. Okay, it returns a tree, it returns an iterator. We want a tree iterator. So we cast it into a tree iterator, and then we're going to do iterator set iterator dot set pre-order. We're going to pass it, we're going to walk through the tree in pre-order manner. This out. Pre-order and show iterator, not show iterator contents. So we want to show what's in the iterator. So we're going to write a method in here, public static void show iterator and tree iterator. We're going to pass that over here. And all we're going to do in here, we're going to create a person. We're going to go through the iterator, and we're going to get all the people that are in the iterator and show them one at a time on the screen in the order in which they show up in the iterator. Okay, is equal to null. And then we're going to do this int num is equal to 1 while my iterator, while iterator dot has next. I'm going to get the next item out of the iterator. Okay, so I'm going to say person. That person is equal to iterator dot next, which gives me a tree item. Dot next. Okay, and then from what the tree item that it's giving me, I want to get the value. Okay, the tree item has a key value. Okay, I want to get the value out of it, and I'm going to say sys out and num plus plus comma plus sorry plus person. Okay, so we're going to do this for all of the different methods of walking through the iterator. Okay, so show, so we're going to show iterator, show iterator, but there's not multiple show iterators. Show iterator. Okay, my iterator, yeah, the iterator that I'm passing in. And then I'm going to do in order. In order. Okay, and then I'm going to do post order so we can see the iterations in the different ways that they show up. Post order. Okay, and I think that's all we're going to do for now. Let's run this. Let's hope we didn't break anything. So let's run this. Oh, we're not calling our traverse method. Haha. No wonder. Traverse. And then pass in the tree that we have, which we called it BST. Right? That's what we call the tree. So let's run. Oh, we have a null pointer exception. We have a problem. Java lang 22. So it's saying that I'm not getting an iterator out of the binary search tree. Let's see why I'm not getting an iterator. Did I not create? Did I not call the implements iterator? So iterator. Iterator. Oh, we didn't do the iterator. No wonder. So we have an iterator. We created an iterator, and we called it a tree iterator, right? And the tree iterator is created by passing in the binary search tree, okay, to the iterator. So we're going to do in here in the binary search tree iterator. Return tree iterator, and we're passing in, yeah, it's going to be of that type. return a new one of these. Sorry. Return a new tree iterator, which takes in self. You know, I'm passing in my binary search tree into it, okay? And the binary tree, the tree iterator takes in a BST, binary search tree KV, and over here, and why is that an error? I don't understand. We want to, it needs to have these particular parameters. And I think it does. So let's cast it to an iterator in this case. I think it might. I don't know what the problem is. That's not the problem. Let's just go back and look at a tree iterator. What does it take? It takes a binary search tree as a parameter for the constructor, right? That's what we pass it in. So when we are creating a tree iterator, comparable or super V, okay. This, not self. It's called this. Self is a different language. Sorry, my bad. It should be the same. I'm not understanding what this error is. Generics can be a pain. So K extends comparable or some super of K and then a V. Anybody can see what this error is? I have no idea what this error is. Incorrect number of arguments to tree iterator. It cannot be parameterized with arguments. K. Oh, did I put a comma in here?
Didn't originally have comparable.
I don't. I see what the problem is. I don't have to say all of this.
Okay, right?
It just needs to be KV. All right, never mind. So, all right, let's try running it now. Okay, pre-order, post-order. Okay, so in all of these, we're printing pre-order, so we don't want to print pre-order.
That's in the driver. You had to change in the system.out.
In the system.out, pre-order, in order, and post-order. Post-order. And now let's look at the tree iterator. What happens when we set in order? BST get root, pre-order, has next, tree is empty. If this.pre nodes is equal to return false. Okay, so we set pre-order, this.post-order, and we said that the pre-order and the post-order are all written over here. Has next, in order. So it's saying that there's nothing in the tree, but that we know that it's not to be true. So let's go back and look at the driver, see if we forgot something. In here, BST insert. Okay, did our BST have a size? Okay, is empty. This root is equal to null. Okay, insert is insert item. So we are inserting a bunch of things into the tree, but it's not showing up in the iterator. So show iterator. While iterator has next, person iterator get value, system.out plus person. So, and why does that not print? So let's put something in the iterator over here just to count how many items we're putting into the node, right? Has next. Pre-order, this not pre-order. Sys out. This nodes in the tree equal to plus this dot tree nodes. Dot tree nodes dot size. Okay, just want to see how many nodes are in the binary search in our iterator. Okay, when we formulate it. So there are 100 nodes in the tree, and why are they not printing? They're supposed to print over here. So pre-order, in order, post order. Okay, so we're getting nodes into the iterator. The question is, why are they not showing up? So let's go back to our driver and show iterator. Set in order. Let's go back and look at the iterator here for a second. Has next. So we created an iterator, set in order, this dot tree nodes. New vector. This dot in order, get bst dot get root. This dot in order. And okay, so has next is probably the problem. Next. Let's see, one of these methods is a problem. I don't know which one it is. This dot tree nodes removed, node 0. This dot tree node element at 0, get tree item. No idea why this is happening. Did I write this wrong over here? While the iterator has next, person get next, get value, and print out the person. Interesting. Okay, we'll come back to this. Let me just figure it out. I don't want to spend a lot of class time on this. I will come back to this. We will fix this and I will show it to you, okay? I don't want to spend a lot of time debugging that right now. There's something very simple going on here that I can't wrap my brain around right now. Tree iterator. We called this tree, right? We passed in a tree iterator. I don't know. We'll have to come back to this. So I don't want to spend a lot more time on this right now. But what I do want to do is I want us to go back and look at the structure of a tree and figure out the fact that this tree lends itself to recursion. Because when you look at a tree, and here we'll look at a tree together. If I have this tree over here, 25, 15, 35, 10, 20, 30, and 40, okay? Like I said, trees are recursive. Why are they recursive? Well, let's take a look at the fact that this here, the big tree rooted at 25 is a tree. This tree has two subtrees. This tree is a subtree of the big tree, right? And every tree, every node in the tree has two subtrees, okay? The two subtrees of 25 are the tree rooted at 15 and the tree rooted at 35. The two subtrees of 15 is the tree rooted at 10 and the tree rooted at 20. The subtrees of 35 are the tree rooted at 30 and the tree rooted at 40. And to continue with that, okay, the tree rooted at 10 has two subtrees. They're both null, right? Has a null left tree and a null right tree. Null, 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 null. So this is a repetitive, recursive structure, okay? We should be able to take advantage of that when we are writing code to manipulate binary search trees. We have written all of the code for the binary search tree so far so that it is not recursive. The only thing that we wrote in recursion was the iterator. And we'll come back to that, okay? But when I look at my binary search tree, I should be able to insert and find and delete in a recursive manner, okay? And we'll find that in doing so, what we do is we make the code a lot simpler, okay? So let's take a look at what we did. Three methods in here in the binary search tree. We did three methods. We did insert, we did find, and we did delete, okay? Those methods, we're gonna change the private methods for them to be recursive, okay? So what we're gonna do is I'm gonna comment out these methods and their private counterparts, okay? So this is the insert method that gets called, okay? That's the find method, and that's I'm just gonna comment out all of these, okay? Compare keys, I'm not gonna, okay? So we're commenting out all of these non-recursive methods that we had. And we're gonna do insert in a recursive manner, okay? We're gonna do insert in a recursive manner. So the insert in a recursive manner calls a private method. So let's do that. Public void insert. Okay, and insert has the following parameters. Okay, it just calls insert, and it has it takes a tree item. Okay, it takes a tree item to be inserted. Okay, and it calls a recursive method that is private, and we're going to write that. But first, let's write the call to it. The call to it is this dot insert, and we're going to call that method item, insert item, and it takes this dot root as a parameter, a null, okay, and a tree item, okay, because null is the name of the parent, okay, and this method returns to you this dot root. Always gets done that way. Okay, so let's take a look at what this method looks like. So private tree node, it's going to return a tree node, KV, insert item, and it takes the following parameters. It takes the following parameters. It has the node that is where we're inserting into tree node, KV, KV, the node that I'm working with, its parent, tree node, KV, parent, and the item that I'm trying to insert, tree item, KV, and the item that I'm trying to insert. Okay, so those are the three things that are passed into me when I get started here. Okay, so what's this method going to look like? Okay, well, what we're doing is we're going down the tree. So let's take a look at a tree that doesn't have anything in it. Okay, so we're going to start out with a tree that doesn't have anything in it. So what is that going to do? So empty tree. Okay, and I'm calling my method over here. And what I wanted to do, if the tree is empty, okay, I wanted to say, okay, the item that I'm inserting is the node, is the root. So I am going to be given an insert, okay, insert, can't write, 25. That's what I'm being given. So I'm going to come in here, and the thing that I want to be able to do is to say, okay, 25 is the root. Okay, that's what I want to be able to do. Okay, so if the root is null in this case, so I'm being passed the root to start out with, I'm being passed the root. So all I'm going to do in here, I'm going to say if the node is equal to null, then what am I going to do? I'm going to create a new node. Okay, node is equal to new tree node, KV, and give it the tree item that I'm trying to put in here. Okay, tree item KV item. Tree item, no, the item that I'm inserting. Okay, That's what goes into that node, okay? And make the node that set the parent, okay, to be the parent. Notice that this has a null being passed in because it's empty at this point in time, okay? And I want to return the node, okay? We're going to do a bunch of other stuff too in a second, but first let's make sure that this is KV, okay? If node is equal to null, not set it equal to, just make it test, okay? So what's going to happen? The first time it gets passed in, it's going to say insert, and it's going to pass in the root, but the root is null, and the parent is null, and the item that I'm trying to insert. So if the node is null, then make a new node, put the item in it, okay? Set its parent to whatever the parent was, in this case null, and then return the node, which gives us this, okay? That we will agree inserted the root. So what happens now if I am given 15 to insert? Okay, insert 15. 15. Well, clearly I want 15 is going to have to be to the left of 25. Okay, so I want to ask the question in here. I'm going to ask the question in here if this that compare keys, and the key one is going to be equal to whatever the node is that I have, in this case the root that get tree item that get key, and then key 2 is the item that get key. Okay, the two keys that I want to compare. And I'm going to ask the question if it is greater than 0. In other words, is the item in my node greater than 0? Okay, is the item in the key of my item that is in the node, because in this case, they're passing me the root. The root has 25 in it. The root has 25 in it. So I'm comparing 25 to 15. Okay, and that tells me that 25 is bigger than 15, so it's going to be greater than 0. So I need to go to the left. Okay, and the way that I do that is I would say node that set left child to be the result of the insert item, and what I'm going to pass in here is node that get left child, and then pass myself in as the parent, okay, and the tree item that I want to insert. Okay, that's what I'm going to do. So item, it's not tree item, it's item. So what am I doing in here? Can't have two E's in insert. Okay, so I'm calling myself, and I'm saying node is currently equal. So if I'm looking at my stack of recursion, okay, node is equal to 25 at this point, right? Because I called it and I passed in the root, okay? And I'm asking in here, if the key in this node is bigger than the key of the item that's being inserted, then I'm saying set the left child of this node to be whatever returns from the method insert item, and I'm passing in the next time in here, the node, what's the left child of this particular node, 25? It's null, right? And the parent in this case is null, but the parent now, when I call it, the parent is equal to 25. That's who the parent is the next time around in the method. I come around in the method and I go into it again and I say, if the node is null, and the node is null, okay, well, it says create a new node. So I'm going to create a new node, put the 15 in it, okay? I'm creating a node, put the 15 in it, okay? Set the parent, because that's what I'm doing in here. Set the parent to be whatever the parent was passed in. The parent was passed in as 25. So I am going to set the parent to be 25, okay? And nothing else. I'm going to return the node. So when I return the node, it comes back to the 25 that called it. And in this case, it sets the left child, which means this becomes the left child of that. Okay? Else, if I'm not going left, I must be going right. Okay? Else, node.set right child, node.set right child, and then get the right child. So when that finishes, when this method finishes for the 15, it returns, right? This particular instance of the method goes away and it returns, right? And it returns, and when it returns, it sets the left child, and then it returns the node, which is the root, okay? And the root is always the root. It will always get reset back to whatever the root gets returned, okay? And if I'm inserting 35, insert 35, I'll come in here, I'll start out, I'll call with the root and the null and the tree item. That's this call, and in this method, that's that stack frame, and then I will compare the keys. 35 is not smaller than 25, so I'm going to go to the right, get the right child of the root, which is the node in this case, of the right child of the root is null, and the parent is going to be the 25 again, right? And then I go back into this method. If the node is null, create a new node, put the 35 in the node, okay, set its parent to be the node above you, okay? That's what set parent does over here. And then I return. And I return the node itself, 35, right? When I call the node, when the node that returns, it's going to come back over here, which basically sets the right child to be that node. Sets the right child to be that node. Let's try one where we're going to go too deep, okay? So insert now, insert 10. Well, I start out at the root. And 10 is smaller, so I go to the left. So I'm calling node. The left child is 15, and the parent is 25. I come in here. The node is not null, so I try again. Is compare keys. 10 is going to be less than 15, so I'm going to go to the left of 15. The left child of 15 is null. Node null. Parent is equal to 15. And when I come into here, I create a new tree node. I put the 10 in it, and I set the parent to be 15 because that's who the parent is. And then I return the node that I just created, and that sets the left child of 15 to be the 10 node. Okay? And this is a recursive way of doing things for the tree. So notice that how much shorter this was the method for inserting before in non-recursive manner. This is inserting in a recursive manner in a binary search tree. The advantage of recursion in these kind of situations is it usually is much more simplified code to do the insertion. Okay, any questions about how this method is working? Okay, find item was a method that was not recursive for us. We're gonna make it recursive ourselves, okay? So we're gonna find the item. So public find.
All right, quick question, Professor.
Uh-huh.
Are you making these methods recursive because of the output that we were getting before, when we had the methods written the way we had them, or are you showing us the recursive version for these methods just to show, or not to just show, but for teaching purposes?
It's teaching purposes that I want you to see the recursion, because you're going to have to write some recursive methods here, okay? And we're going to discuss those, like things to find the height of the tree, for example, and stuff like that. Those are also recursive in the way that they work, okay? So I just want you to see these in order to be able to do the recursion yourself, okay? Is that okay? That answer your question there,
Yeah, no, you did. Yeah, I was just trying to make sure. Thanks.
We're just trying to redo them in a recursive manner so that we could do this. Trees by nature are recursive, so I want you to be able to do the recursion, okay? So again, the recursive method in here is going to be, we're going to call the private method return this that find item, and we're going to pass the key that we want to find, okay? But we're not just passing the key, we're also passing the root of the tree that because we're going to start at the root, okay? Tree node kv this dot root and the key, okay? We're going to pass that into the methods, to the find method. We don't have that method, okay? We don't have that method. I don't need to say tree node because it knows it's a tree node, okay? So let's write the method find item in a recursive manner. So private, so the method that we want to write is a private, and it returns a tree item if we find it, right? Find item with the key, and it takes in a tree node, kv node, and k is the key, okay? That's what this method takes, two parameters. If I navigated in the tree far enough that I got into a place where, because if I'm looking for something in my tree, okay, if I'm looking for something in my tree and I look at, let's say I'm looking for 5. Well, it's going to be less than 25. It's going to be less than 15. And it's going to be less than 10. So I'll come to be who's the left child of 10? It's going to be null. Therefore, 5 doesn't exist. Similarly, if I'm looking for 45, it's going to be greater than 25, greater than 35, greater than 40, but the right child of 40 is null. So if I ever get to the point where I looked for something and I hit a node that is null, then I'm just going to return null. So I wasn't able to find it, okay? So if the node is equal to a null, then just return null. I didn't find it. Okay. Else if this dot compare keys, and the key is the node dot get item dot get key, and the other one is the key. And I'm saying if they are essentially the same, if they are the same, then I found the thing that I'm looking for. Okay, if the keys are the same, the key that I passed in and the key that is in this node, if they are the same, then I found the item. So I'm just going to say return, okay, node dot get tree item. Okay, just return the item that you just found because we found it. It has the same key as the one that I'm looking for. Else, if this dot compare keys of node dot get tree
No, you're
item.
not trying. There's a sound prank.
Yeah, no,
Oh.
that's like the intro.
Kelvin, would you mind muting yourself? Thank you. And the key that I'm looking for, if I'm looking here, and if that is less than 0, that means I have to look for it over on the left, right? I mean, no, if it is greater than 0, it means that this current node has a bigger key than the key that I'm looking for. So I have to go to the right, to the left to go look for it. So I'm going to say return find item. Okay, node dot get left child, right, and pass in the key. Else, it's going to be to the right. I'm going to say return find item, node dot get right child, and the key. Okay. This dot compare keys. And we
I
need to
think
get,
it has an S. Like the method, it's the, oh, never mind.
okay. So what was that? Did I just fix the problem you were about to talk about, Ajani?
No, I thought the problem was like, I thought you spelled the method wrong, but I realized that wasn't an issue.
Okay. So what's going on over here? Well, let's take a look. So if I'm looking for the number, the key 20, okay, if I'm looking for the key 20, what's going to happen here? Well, I'm going to come in and let's do the stack, my programming stack, my call stack. The first thing I'm going to come in here when I call it first, I'm going to pass in the root and the key, right? So the node is going to be equal to the 25 and the key is going to be equal to 20. I'm looking for 20, right? So I'm going to look. Let's see what this method does. If the node is null, nope, the node is not null, right? It says, okay, well, compare the keys. Is the key in this node equal to the key that I'm looking for? No, it's not. Clearly, 25 and 20 are different keys, right? And it says, all right, well, if the key of the node is bigger than the key that I'm looking for, then do the same thing, but go to the left child. Okay, go to the left child. So what's the left child of 25? It's 15, right? So it says node is equal to 15, and the key is still 20 I'm looking for, right? And it says, all right, node is not null. Is the key 20 smaller than 15? No, it's not. So go to the right. I'm going to go to the right now. And it says the node now becomes 20 and the key is 20. Okay. And now it looks at it and it says, okay, is it the key, the item, is this key and that key equal? Yes, they are. So return the tree item. So this is going to return 20 to here, which then returns 20 to here, the item, and then that returns 20 to wherever it came from. If I don't find the item I'm looking for, I am going to return null. Okay, so if I'm looking for 25. I mean, if I'm looking for 27, I'm going to find it to be less than, greater than 25, less than 35, less than 30, but there's nothing less than 30, so that will return a null. Okay? So that pretty much explains that particular pass right there. If you just give me 1 second to look something up before we continue. The next thing that we want to do is delete. Okay? The next thing that we want to do is delete. And so we're going to do that next. And hang on 1 second. I just need to. Just give me 1 second. Insert item, delete node. Okay, so sorry about that. Any questions about the find and the insert? They're both pretty straightforward recursive methods. The next method that we want to write is the delete method, the delete a key. Okay, and for that we're going to write the stub method over here. What happened over here? Why am I having an error? Oh, I don't need to specify the type. Just need to pass it in. I keep making that error. Why is this an error over here? Oh, it's not a void. It returns a tree note, a tree item. It returns a tree item. KV. Okay? It returns a tree item. That was the error. Okay? The next method that we want to do is delete. So public void delete and the thing that we are deleting is something with a key. Okay, delete the item that has the key, this following key in it. And for this, we're going to say this dot root is equal to this dot delete item. And the thing that we're going to pass is this dot root and the key. Okay, and let's write that method over here. Private tree node is equal to tree node KV delete item, and it takes both a node, a tree node, KV, node, and key. Okay, and we want to be able to write this code in a recursive manner. So let's do that. Delete the item. So if the item, I'm going to try to find the node to delete. Okay, that's the first thing that we want to do, is we want to find the node to delete. So we're saying delete at the call in here. We're saying delete the item starting at the root. Look for the item to delete starting at the root, and find the item that has this particular key. And then whatever this method returns is going to be the root. Okay? Because if I'm deleting the root, then one of these other nodes is going to become the root. So I need to know who the root is. So I set it to be the root. Okay? Remember, if I am deleting the root, then I have to set somebody else as the root. Otherwise, my tree does not have a root. So that's why I return something over here. So if I encounter a situation where if the node is equal to null, in other words, I did not find the node that I'm looking for, it is not there, okay? I'm going to throw an exception, okay? I'm going to throw an exception. And this method, delete item, throws a tree exception. Tree, did we not create a tree exception? Yeah, we did create a tree exception, no? We did create a tree exception, but so let's go back here and tree exception. It's saying that there's, oh, because it throws a tree exception. And what is a tree exception? So throw new tree exception and just say tree exception item to delete was not found in the tree. Okay, that's what we're going to say. If it was not found, that's what we're going to say. Else, okay, we're going to keep looking for it. Okay, to delete it. Okay, I'm going to go to the node that I am at, tree item, KV, and it's going to be the item that's in that node is equal to node.get tree item. Okay, get the item out of the tree, out of that particular node. And then now I want to compare the keys. If this dot compare keys, and the first one is item dot get key, and the other one is the key that I have. Okay, if they are equal to 0, that means I found the item. Okay, I found the item that I want to delete. That means now I delete this particular node that I want to delete. Okay, that's what I'm going to do. All right, we haven't written that delete node, but let's write the rest of this recursion first, and then we'll come back to this. Okay, if else, if this dot compare keys, item dot get key, and the key are greater than 0. If they are greater than 0, that means the key in the node is bigger than the key that I'm looking for. So I want to go and look to the left of there, right? I'd say, in this case, node that set left child. This is very much like the insert, except we're deleting. When the deleting, we might change the left child and the right child. So set the left child, and we're going to say delete item node.get left child and the key. Okay. Okay. And key. No, oh, we have to specify what kind of element key is, and that needs to be a capital K. Okay. So note that set the left child, and then I'm going to say in here if node that get left child not equal to null, node that get left child dot set parent to be the node itself. Okay. After I've set the left child, I want to go to the left child and tell him to tell him who his parent is. Okay. And here we're going to say node dot set right child, delete item, delete node, delete item, node dot get right child, and the key. Okay, and then coming back, if node dot get right child not equal to null. In other words, after I finished, do I still have a right child? And if I do, then tell the right child node dot get right child dot set parent to be equal to the node. Okay. We haven't written the delete node yet. Okay. So what am I doing over here? Let's take a look a little bit at this. Okay. Let's take a look at this. So let's take a look at the case where we only have a root. Okay. There is no left child. There is no right child. Okay. There is no left child. There is no right child. So there's just a root, 25. And somebody says delete 25. Okay. I come in here. I say, are the keys equal? Yes. Then delete the node. Okay. Then delete the node and return at the end over here. There needs to be something to return the node. Okay. So I come in here and I say, delete the node that I'm trying to delete. Delete node returns something, and it returns a node when we say delete node. We're going to see why we need that. Okay. We're going to see why we need that. And then we return the node. Let's write the delete node method first and then walk through it. Okay. Let's write the delete node method first and then we'll walk through it. So let's write that. That's down here. Private, delete private, and it returns a tree node. KB, delete node, and a tree node KB, and the node that's being deleted. We found the node that we want to delete, and what do we do with it now? Okay, so we're going to ask the question, if this is a leaf node, we have a bunch of methods in here that do this for us. So let's copy, let's uncomment these. Has no right child, has no left child. Okay. I think let's uncomment these. Okay. We're going to need these. And we're going to recomment back the ones that we don't use. Okay. So we're going to ask the question, if this is leaf node, the node that I have, then what am I doing? No children. There are no children to this node. So I'm just going to return null. Okay. I'm just going to return null. So now going back to my tree that only has a root in it. Okay, notice that when I call delete node over here, and I call delete node, delete item, okay, delete item returns to me a node. Okay, so here, 25, I'm trying to delete 25. Is it a leaf node? Yes, it is a leaf node. Okay, so what do we do when it's a leaf node? When we do this delete, it just returns a null, which means node in here is set to null, which means it returns null, which means it returns a tree to its null state. So the root then is gone. There's no 25 in it. Okay, there's no root. So the root is null. That means the tree is null. But if I have 25 and I want to 15 and 35, okay, and what was it, 10 and 20, 30 and 40, okay, we want to try to delete a node that has no left child. Okay. Okay. So let's do that. No, left child. All right. So let's take a look. So if the node is null, then I just return a null. Okay. If it's a leaf node. Else, if it's not a leaf node, okay, I want to know else if this has no left child. Has no left child. Okay. Then I want to return node that get the right child. Okay. So if I'm trying to delete the node like 35 in this case, if I look at 35 and I say it doesn't have a left child, let's get rid of its left child. I'm trying to delete a 35. I find the 35. We're going to find it in a second. We found the 35. It has no left child. So I want to promote his right child to be himself. Okay. So I'm just going to say return the right child. Okay. Which means the node that gets here returned will be the node that is the right child. Okay. So what will end up happening is 40 will move up here and that goes away. Okay. So, and then the same thing happens if the node has no right child. I'm going to promote the left child. And if that left child or the right child happens to be null, that's not a problem. Okay. Because then just we're setting them to null. Else, if this that has no right child and has no right child, the node, then return node that get left child. Okay. That's what we're going to return in here. Otherwise, it's not a leaf. It's not a single parent. It's not a parent of a single child, only parent of an only child. It has two children in this case. We're going to find the successor. Okay, we want to find the successor, which is what we did before. Okay, so this is successor. We're going to find it we're going to write a tree node, KV, successor is equal to this that find successor and node dot get right child. The successor, remember, is always going to be to the right, the leftmost child of the right child. Okay, the leftmost child of the right child. Because if I go back to here in the tree, if I'm trying to remove 25 from the tree, his successor is 30. 30 is the leftmost child of the right child of 25. So you go to the right child of 25 and then you go all the way to the left. Okay. And let's write the method find successor. We're going to write it over here. Private tree node KV find successor. Tree node KV node. Okay, and the way that works is we keep going to the left until we can find the successor. So we're going to say in here, if the node that get left child is equal, if it doesn't have a left child, then it is the successor. Return the node. Otherwise, then return the find successor from the node that get left child. Keep going to the left until you can't go anymore, and then return that node that you find to be at the extreme left. Okay? Find successor. Okay? That finds the successor node. Okay? So I'm going to make the successor, since I'm getting the successor, I'm going to make the node that set tree item to be the successor, whatever is in the successor dot get tree item. Okay, so if I'm deleting 25, I find the successor to be 30. So what I'm doing in here is I'm taking 25 out of here and I'm putting the item in here to be 30. Okay, now what else do I have to do? I have to go back and so I have to go back now and delete the successor node, right? I have to delete that successor node 30, right? So, so what do? I then say node that set the right child of this particular node, because if he's the only successor, if 35 was the successor, then I got to change who the child of 30 is, right? Because he's his own. So if the tree looked like this, 25, and it had only a right child of 30. Okay, I have done this so far. I have put the 30 in here, and now I want to remove the right child. It has no right child anymore, but I got to delete the successor. Okay, so the successor. This dot delete node. Okay, node dot get right child. So delete the node that has delete successor node. So we have to write not delete node, delete successor node. Node that get right child. So we're going to need to write this method, delete successor node, private, tree node kv, delete successor node, tree node kv, and the node that I want to delete. And how does the delete successor node go? If node.get left child is null, if node.get left child is equal to null, then return node.get right child. Okay, so if the successor doesn't have a left child, okay, of course it won't, then we're going to return its right child. Else node dot set left child to be this dot delete successor node dot get left child. And that is a lowercase this. Okay. And then return the node. Okay. So how does that work? Node that set right child. Get right successors, set 3 item. Child. Node that set right child. This that delete successor node that get right child.
Professor, can the error be the return that's after the else?
Where? In here?
On top, it says else, and then it says return find successor, and then it says node dot set.
Return find successor. Yeah, where oh, up here in delete find successor. Huh? In this one here? Is that
Yes.
right here?
Mm-hmm.
Okay, so maybe that's wrong. Maybe I wrote that wrong. Find successor. Return. Okay. That's not right in here. You're right. Okay. This should be, that was supposed to be in here. Sorry. Okay. That's where that was supposed to be. Thank you very much for that, Zahra.
You're welcome.
So how does that work? How does that work? Is that all of it? I think that's all of it. Find successor, is leaf node, not, has no left child, has no right child, has right child. So this one is not used. So let's comment it back. And has left child. So whoops. This one is not being used. And this one is not, whoops, again, has no parent, is also not being used. Okay, so so let's walk through this delete item. Okay, let's delete a node from our tree that has 2 children. Okay, so let's go down here and let's delete the 15. Let's go back to our full tree. Okay.
Professor, we can't see.
Let's go back to our full tree. Thank you very much. 25,
Problem.
35, 30, and 40. I want to delete 25. Delete 25. Okay, delete 25. Okay, so we come in here, delete, and it says delete this. So our recursion stack for the delete starts out with saying delete item. So I'm going to say delete item is what this method is called, delete item. And I'm passing in the root, the node is equal to 25, and the key is equal to 25. Okay, that's what I'm trying to delete. So let's go to delete item. That's going to be, if this is the item that I wanted to, if the item, get the tree item out of the thing, is the key equal to 0, right? Just know that I found the node that I wanted to delete. So I'm going to now call delete node. So this is delete node, and the node is equal to 25 that I'm passing in. Okay, that's what I'm passing in from here. Okay, delete node, and I'm passing in node 25. So now I'm in delete node. Okay, is this a leaf node? No, it's not a leaf node because 25 is the root and it has 2 children. Okay, does it have a left child? Does it has no left child? No, it has a left child. Does it have a no right child? No, it does not have a no right child. Okay, so then we come to this piece of code right here. Okay, find the successor. Okay, so we're going to call find successor. Find successor is what this method is now. And find successor is going to say of the right child. We're passing in the right child. So find successor of the node is equal to 35. Who's the successor of starting from 35? Find the successor. Okay. How does the successor work? Successor says node, if node.get left child is null, no, 35 is not null. So then you say find successor again, okay, by going down to the left child, right? Go to the left child. So node is equal to 30. Now I'm in find successor. And it says, does this node have a left child? No, it does not. So it says return the node. So now we are returning 30. Okay, I'm returning 30. And then that returns a 30 over here. So the node that the successor is 30. I know that. And those methods are finished down here. Those methods are finished. We found the successor. We know who the successor is, and we have set it. The successor is here. It's been defined. Okay. Get the successor out of the item out of the successor. Okay. And then you're going to say node.set right child. Okay. Delete the node, find the successor. Nodes, delete the nodes. This that find the successor. Okay, we found the successor, and we're back at the delete node. And the node that we're trying to delete is, and this also returned. Sorry, this returned also 30 from here. So the successor is over here, not in the delete node. No, it isn't the delete node. It isn't the delete node. Okay, so in the delete node, find the successor, and the node is 25, and the successor is 30. So set the tree item. So now this here becomes a 30. Okay, in the node, in the root, that becomes a 30. Okay, that's where I'm at. And now I continue from here. Let's move this to the side so we can see all of this. Okay. So I found the successor, and I'm going to say node set the right child by deleting the successor. Okay, by deleting the successor. So set the right child of this node, okay, by deleting the successor. Okay, so delete the successor node. Okay, if node, so now I'm in delete successor node. Okay, I've come down here. I'm in delete successor node. Delete successor, and now what I'm passing it is, what am I passing it? Get the right child. Okay, so I'm down here, and the node is 35, right? That's who my right child is. All right, and now delete successor says, if node.get left child is equal to null, then return that, okay? Return the get right child. Otherwise, note that's if the get left child is null, 35 does not have a null left child, so we're not going to do that. It says node dot set left child, okay, by delete successor node go dot node dot get left child, okay. Delete successor node is equal to 30, okay, and it says okay, delete this left child of mine, okay, and whatever it returns, just make that. So I go down to 30 now, and 30 says, does this node have a left child? No, it does not. So I'm going to return the right child. The right child is null. That returns a null, which basically sets the left child, okay, which basically sets the left child to be null. So that basically removes this node out of the equation, okay? And then that basically sets the tree up in the way that we want it to be set up, okay? So these are the methods for deleting and adding and finding nodes in a tree in a recursive manner. Now, why am I teaching you this recursion? Why is this important, the recursion? We're going to answer that question after we come back from attendance, taking attendance. So I'm going to basically pause the recording now. And why do you think we're doing all of this recursion? There's a bunch of stuff that we want to know about trees, okay? And one of the things that we want to know about trees is their height. We want to do a couple of things that we want to know about the trees. One of them is the height. And what did we say the height is when we talked about it early on, when we talked about the height of a tree? The height of the tree is the distance between the root, counting the number of levels, starting at the root, okay, of the furthest away leaf node. Okay, the furthest leaf node from the root in this particular example that I have over here is this one. And this is the root. So what is the height of the tree?
Professor, we can't
Professor, do
see.
you have the screen? Can you share your screen?
I am not sharing the screen. I thought I was sharing the screen. Let's go back to that. Sorry about that. Okay, so this is the tree that I'm looking at. Okay, and the farthest node is down here. This is the farthest node from the root up here. Okay, so I want to know what the distance is from here to there. Okay, I want to know the height of this tree. Okay, and we said the height of the tree, a tree with only one node has a height of 1. A tree with a one node and at least one child has a height of 2. Okay, and this has a height of 3. Okay, so this height over here, so this is height of 1, that's height of 2, height of 3, 4, 5, 6. So this tree has a height of 7. Okay.
Wait, Professor,
Yes.
when you say the node that doesn't have a child has a height of 1, isn't it a height of 0 actually? Because there's no.
There's 2 different ways of defining that. We said that early on. The book defines it as a height of 0. We're going to define it as a height of 1.
Okay, all right.
Okay.
Sorry, I was just because that is what the book said.
That's what the book said. You're right about that, Johnny. But we're going with the algorithm. There are 2 different ways of looking at this in computer science and trees, and both of them are acceptable.
So then, as long as the tree exists, at the very least, it should have a height of 1.
Right.
Right.
A tree with no nodes in it, an empty tree has a height of 0.
Okay, yeah, that makes sense. All right.
Okay.
Hello, Professor. I'm sorry.
Yes, Caitlin.
Yeah, I was typing in present, but my kind of frozen.
It is, so you were here, but
Yeah, I was here the whole time. I was listening to you, but I was typing in and it didn't go through the frozen.
okay, we'll mark you present, Caitlin.
Thank you. I appreciate it, Professor.
Sure.
Thank you.
Okay, so a tree with no nodes in it, okay, is it's got a height of 0. A tree with one node in it has a height of 1. Okay, so height is important in a tree. Why? Because we want to know the expanse of the tree, like how much stuff is in this tree. If this was a full tree, okay, if this was a perfect tree, then it would have all these other children in it, right? Correct? Each one of these would have children, so on and so forth, going all the way down, so on and so forth. We get some kind of a notion of how many elements are in this tree, okay? But this tree is not a full tree or a complete tree or a perfect tree, okay? We want to know its height because we want to know something else about the tree. We want to know if a tree is balanced, okay? Did we discuss balanced trees before? A balanced tree, okay, rooted at R, okay, is balanced I can't spell balanced. Balanced if height of left subtree and so height of left subtree and the height of the right subtree okay, if HLS minus HRS absolute value is less than 1. Okay, what does that really mean? It means root R, then I have a left subtree, okay? The left subtree is this one. Everything to the left over here is the left subtree. So let's make a left subtree over here. And let's make a right subtree. So that's the right subtree. So this is the left subtree, and that's the right subtree. Okay? And let's measure its height. Okay? So what is the height of the left subtree in this case?
3.
Say that again, sorry.
3.
3. Okay, so height of left subtree is equal to 3. And what's the height of the right subtree?
4.
And that's 4. Height of right subtree. So HLS 3 minus 4 absolute value is less than or equal to 1. Okay, it has to be less than or equal to 1. So we say that this tree is balanced. Okay, because the difference in height between the left subtree and the right subtree is no bigger than 1. Okay, why are we interested in that? Why are we interested in that? Because if we end up with a degenerate tree, a tree that is not a tree really, okay? So I give you the numbers 3, 4, 5, 6, 7, 8. They're gonna get inserted into this order, into the tree. Is this a balanced tree? No, because the left subtree has a height of 0, and the right subtree has a height of, starting from here, right? The height of the 1, 2, 3, 4, 5. So this tree is not balanced because the difference between the left and the right is bigger than 1. So this tree is not a balanced tree. Balanced trees are important because if it is a binary tree and a really reasonable binary tree, okay, finding the number 8, okay, finding the number 8 will be much faster, okay? If I'm going to find the number 8 here, I have to go through 1, 2, 3, 4, 5 times to get to number 8, okay? But if this was put into a tree that looked like this, 4, 3, 6, 7, and 8, finding the 8 is going to be fewer hops to get to it. Okay, this tree is balanced because the left subtree has a height of 2, the right subtree has a height of 3. So this tree is balanced. Okay, it may not look like much. This is 1, 2, 3, 4, 5 steps, and this was reduced down to 1, 2, 3 steps to find the 8. Okay, so we want our trees to be balanced because it makes the operation of searching to be much faster. Okay, and on Wednesday we're going to talk about how to calculate. We're going to finish this code, and I'm going to debug what I was doing wrong over here, and then we will debug this and finish it and talk about height and how to create a balanced tree from an unbalanced tree. And your assignment is going to be essentially that. You're essentially going to be required to figure out the height of a tree and figure out if it's balanced. And if it's not balanced, there's going to be, you're going to write a method to balance the tree. Okay. So any questions before we let go and come back here again on Wednesday? Any questions before we say goodbye?
No question, Professor.
Professor, I have a quick question. This pertaining to all that. I was just wondering if anybody had taken the 3 o'clock slot. Because the last time I checked, I didn't see anybody take the 3 o'clock slot.
For today?
Yeah, for today.
No, there's nobody at the 3 o'clock slot.
Okay. Just wanted to know. All right. Thank you.
Did you want to start early, Johnny, or?
Yeah, I guess we can since nobody, or I guess leave it up to anybody who wants to take the 3 o'clock slot. I don't know, but I wouldn't mind starting early if nobody else wants it.
So you know what? I'll start 5 minutes early with you because I have something to do until 3:10. Okay. So how about we start at 3:10?
3:10. All right. Yeah.
Okay. All right. I'll see you guys on Wednesday. Take care. And I'll see you back. Bye.